that either worked with Cursor, Gemini, Windsurf. There's a lot of products out there. We've also seen how our research can be utilized in these products. So there's a lot to discuss here, but I'll really focus a bit more on the previous work and how there are opportunities in our group too, which we are currently working on. So first of all, I'll present 3 bigger works we've done. The first of which is focused on just issue resolution itself, which is, as you're quite familiar probably with. You have experience and you do this every day. The second one is more focused on security vulnerabilities and how we can use agentic systems to solve them, how to present patches which developers can then review and then can utilize. We've already had success with that. And the third step, which has been the more broader vision in the past year, which is this universal software engineering agent, where we don't go fully free like Cursor would do, but we still have a system that can decide what step to take, but these steps are still concretely defined, which makes it easier to understand, easier to interpret, and easier to utilize in production. Now, let's start with a very simple problem everybody is familiar with. You are writing code or you want to work with some repository, but you come up to a bug. So you're going to write a natural language description of the problem and give it to the authors and say, hey, I have this issue, there's a problem, I can't make it work. I was expecting something different. Now, what the developer usually would do, they are going to have to look into the code, understand the issue, reproduce it, and say, hey, here's a patch, this is how it's fixed. Now, this takes time. The patching software takes time. Understanding even something you wrote a couple of days ago is going to take some time. So seeing how LLMs can already write code, we asked the question of, can we do LLM-driven issue resolution? So we want to figure out how to make an LLM interact with a large code base, and can software debugging techniques help these LLMs? Because it's not as simple as giving the whole code base to the model. Up to 1 year ago, we weren't able to even fit 100,000 tokens. So that's not the best way to just throw the whole code base. And we see that language models are not able, even with this much context, to properly reason over it. So we really need to give it the right space for work. So the work for this is called Autocode Rover. It's done by a couple of colleagues in our research group, where the focus is as such. Generally, software repair is in a very high level setting, focused on 2 big steps. First of which is having an issue. We want to collect the context needed to solve this issue. And then having sure that we have collected sufficient context, we want to construct a patch that can be applied over the code base to solve the issue. This is from a very high level perspective. There have been multiple steps. There have been a lot of techniques applied here. But this is really, if you give it to a person, that's how they would define program improvement. Get the context and generate something new. Now, the thing is that a lot of the agents, the agentic systems around that time, were really looking at the code just as a collection of text. They were looking as a natural language processing problem. So in a way, they didn't utilize any sort of structure to the code base. For them, it was just the file system is just enough, but that's not correct. In reality, a developer, they look as a file as a collection of entities, or there is some structure inside of it. It's the AST generally. Now, to do this, we had set up an agent, in a way which was one of the fundamental agents for the system, which can explore the code base. As mentioned, we have 2 steps, context retrieval and patch creation. So having the issue statement, we can give it to the language model, and the language model can say, I need to find this specific class. I need to find this function. Where is this function being used? Who uses it? How is this class even defined? Or does somebody inherit it? Now, exploring based on the AST has been quite effective because it really allows you to also present the domain-specific entities. So you're not just limited to saying classes and functions. If your language is more complex or in a very different thing, like let's say XML, you really still can utilize this sort of behavior because that's how you communicate with another developer. Now, the idea of this is that we continuously can prompt the agent, the language model, to give a response and say, okay, I want to do X, Y, and Z. I need these, and these are the locations that I expect that will be useful. So in a way, specifically, you can kind of look at it as very simple recurrence relation, where the context is generated by providing the previous context, of course collected from the natural language description, and get the collection of tools. Now having this output, then we can give it to the analysis, which can generate the next step. So in a way, at some point, the agent reading the natural language description is going to say, I want X, I want Y, hey, I see that X has this, I want Z as well. So this accumulation at some point is going to reach, in a way, a fixed point. It's going to be sufficient for the model to say, yes, I have enough knowledge, I'm ready to go, I can give this to another developer, and they should be able to write a good patch for this. That's the expectation. And in a way, this is sufficient for us to create a very simple patch generation loop where you get the locations. You can prompt a model again to generate the patch. Then you can check whether the patch is okay, and if not, you can continuously iterate on this. Now, of course, I'm abstracting away a lot of things. There is a lot of problems of how you would do the diff, validating that the patch is applicable. There's a lot of implementation details that happen here, but in the end, you're able to say, yes, I have a diff that modified the code such that it's syntactically correct, and I can also run the test suite and say, yes, this is good. Now, this is quite nice, and it's a very simple agentic system. The next step is that there is a lot more information that we're not still utilizing. So there's a lot of techniques that have been developed for people that can also be given to a language model, because this is still structured information that it can ingest, it can process. So that's really one of the strong points of natural language models. So one of the things that's quite been commonly developed in the literature has been spectrum-based fault localization. The idea of spectrum-based fault localization is quite simple in reality. The idea is that you have a test suite. By default, if your code base is a reasonably good code base, it should have a collection of tests that describe the behavior and what's the expected output. It has the real answer in it. In a way, in literature, that's called having a proper test oracle. The idea is that you can also track where this test suite, which parts of the code base this test suite touches. So if you have at least one failing test case and a collection of passing test cases, you can generate some notion of confidence, some measure that tells you, yes, this line is suspicious. So this allows us to collect a bit more additional information, which we can pass to the agent for it to decide, do I need more context, or really giving it a head start in the context so it doesn't need to go over and over through the whole prompting, because prompts are expensive. This is a deterministic approach. This gives you some initial information which you can utilize. Now, when Autocode Rover was being developed, there were really two big benchmarks at that point of time, and one of them is still the benchmark. Like almost everybody who's related with software engineering knows about this benchmark at this point, SWE-bench, which was a collection of 2.4 thousand issues from big Python projects, which are open source. So we're talking about Django, AstroPy, NumPy, SciPy, really projects that are being used every day by by millions of people. So one would expect that the issues there are realistic. Now, to compare the work at that point of time, really there were only two other works, one of which is Devin, but also quite a popular tool. At this point, they have been integrated into real production software. They are being utilized in a more semi-autonomous fashion where there is still human in the loop. And SWE Agent, which was one of the first works that I just mentioned previously. That is the work that really focuses on looking at the code base as just a collection of files, and it can explore. Now, to utilize an LLM, at that point of time, really the state of the art was GPT-4. So we started working with GPT-4 Turbo to make it easier. Now, experimental results were quite fascinating. First of all, there was a big difference in the cost because we had a more precise search. Really, the context that we're gathering was more precise. It was really cheap, and we had pretty much, if not a bit better results than the SWE Agent. Now, this really did help a lot, and it was quite effective. Now, results-wise, yes, as mentioned, things were better, but really we wanted to focus a bit more on the SBFL and really seeing what are the benefits. So one of the things is that developers, or usually the way people write these descriptions, they look at them from a very shallow perspective, or really just the bottom saying, okay, I did X, Y, and Z, but they don't know the full stack trace, let's say. They don't care about it that much. So that may not be passed over in the issue description. But utilizing SBFL, we can kind of gather from it And also, one of the big issues with SBFL that it's quite noisy. It's not able to differentiate good if your test suite is not really precise. To put it in one way, it's like you have to have a lot of tests to be able to get near perfect confidence scores, but just some of them give you a good head start, and LLMs can process this. This is just more text for them, not a problem, but they have the, as you know, the emergent behavior capability. Now, upon reflecting on this, we're asking ourselves, okay, we have context retrieval, but also there's another important thing that generally developers do, which is really focusing on the intent, extracting the intent, like what does this piece of code represent? Like what am I expected to do if I want to fix this function? So in a way, can I give guidance from the context retrieval to the patch generation? So this, of course, made us ask the question of, can we extract and utilize explicit developer intent? Can we make the whole system more trustworthy by presenting these additional artifacts of the reasoning? So this whole idea of reasoning, which is now quite popular with test time training, the reasoning, the thinking models, some of these ideas we already had previously, but we're not focused on test time training, but more of just prompting the model to explain itself. Because we also saw that that really did also give positive results. So this made the follow-up work called SpecRover, which is, in other words, Autocode Rover v2, which was really enhancing upon the initial work. Now, the loop became a lot more complicated than what you remember previously, because we also did a lot more exploration for this. So one of the pain points we saw while evaluating Autocode Rover was that, in a way, we are dependent on the test suite of the project, but generally the project will not contain the test. As you know, if somebody finds an issue, you may be given a reproducer, you may not be given a reproducer. So now you're on your own to try to reproduce the example just from what the developer said. So, and as we discussed previously, large language models can generate code quite well. So let's try utilizing that. And we have another reproducer agent. Now, having from the reproducer agent, we can generate the reproducer test, do our usual context retrieval we talked about earlier. But now we have this addition, which is the function summaries, which is really this intent. So now when the agent is searching the code base, it can always give additional information saying, okay, this is why I gave you this function. I want you to work with it and do a specific action, or like, hey, modify this function, or this function is implicitly called when you do this action Y. Now, having these steps, having collected the context retrieval, we can then also generate a patch, which now patch, one extra step we did was really even when we were working on SpecRover, was that we also added the reviewer agent. So one of the problems is, as I just said, we have a reproducer test, but that doesn't mean we can trust it. It also means that the reproducer test may be faulty. So now we have two sources of stochastic behavior. So we have a patch, which may be correct, may not be correct. We have a test which may be correct, may not be correct. So now I have 4 different possibilities, but we have to be able to locate it. So the way we solved this problem was really having a reviewer agent that observes the execution of the test, analyzes the outputs, and is able to say, yes, for this issue description, the patch is correct, the test is wrong though, we have to modify the test. So this sort of interaction allows us to have another loop which at some point will give us a patch that is correct. Now, this in a way is really the whole idea of LLM as a judge, which is quite popular these days when people want to have evaluations based on LLMs. This was quite effective. Now, we have a patch, but also we can generate more patches. So even at that time, we also saw that, okay, what if we generate more patches because the behavior is stochastic, it's non-deterministic. Let's have more patches and then select what's the best one. Let's utilize the LLM as a judge, not just to judge the outputs, but really judge from a space of outputs. So in this way, this covers the whole cycle and can, in the end, give us one final patch that's able to solve the issue at hand. Now, comparing evaluation-wise, again, around that time, we-bench verified came out, which was really the same 3-bench dataset, but now it was manually evaluated by a collection of professional software developers that have said, yes, this issue you should be able to solve without being an expert in the project. Like, this is a reasonable issue that somebody should be able to solve with some amount of work. Around that time, more agents came out, even some of which are pretty much staples for evaluation these days. So we have Autocode Rover, Agent List came out around that time, Aider was quite popular, and SWE-agent. And we saw that the latest version, Autocode V2, was able to beat them again on the SWE benchmark. The idea was that really this was quite effective. Now, yes, one important thing, yes, all of our work is open source. We really strive to make most of it open source and really utilize it. Now, what is another benefit from all of this though? We talked a lot about the acceptance rates and really how useful it is, but there's also this problem of not everything is valid. So is it still useful? Are these leftover patches that are not correct still useful? And we still see that in a practical deployment, sorry, it's been a long day. We still see that precision-wise we're doing a lot better. So our results would be useful for a reviewer and it would be effective. So it's not just sending some random patches for the success rate, and for the rest of them there is some additional artifacts that we're allowed to use. Now, talking about the result of this, really the signal to noise ratio, we also focused a lot about the trust and how we want to get artifacts that can be trusted. So in the past year, our research, specifically Autocode Rover, has been implemented in a production system. I've also been part of the team for that. So one common tool that's used in production alongside the CIs is really static analysis, which allows you to find issues before they go into production, like issues like taints of vulnerabilities, which can cause to user control data being like an XSS attack, or other issues like no pointer exceptions. Those can be found through static analysis. So using the tool SonarQube, which already can find these issues, we've been creating a setup where we utilize the agent to solve these issues. So now the whole idea of trust, really having trustworthy patches and a lot of explanations, we're seeing that they are effective in production. We're seeing how developers can use it, can solve problems, and really save time because the agent is solving the issues for them. So one of the important things about SonarQube is really this idea of clean code, really quality gates, saying, no, you cannot deploy this code to production even if somebody reviewed it. This is bad for our technical depth. This is risky. This is where SonarQube comes in and blocks this, and then the agent says, okay, you have these issues, let me help you solve them, and I'm going to give you patches, so you just have to review them. So now it becomes quite easier. So we've already seen that our research work can be effective in production. It's already in deployment, but that's a separate topic I can talk after this. Now, I've talked a lot about issue management, but I've talked very much about general issue management. Like, there's a whole nother class of problems, which are security vulnerabilities, which are in a whole class of its own. Just to give you some context, vulnerabilities have been growing. I will speculate to say that they will be growing more with the whole vibe coding era because there's not enough guardrails set up currently by developers. We've already seen how in the past months, even Windows 11 had a lot more issues, and I would speculate that it is related to this. Like, somehow the review process is not good enough. But the idea is that really they're growing and they're continuing to grow. So generally, what people are doing for critical software, we're talking software that's being used every day in a lot of machines, like let's say Linux kernel, FFmpeg, if you're familiar with VOC, that's one of the software that's binding it. They continuously test the system by executing it with various random inputs that ensure that there is sufficient coverage, because humans can write only so much tests and humans can only predict so many behaviors. It's better to just bombard the system with inputs, utilize whole server farms just for this. That's one of the things Google does. If you're not familiar with it, it's called OSS Fuzz project. So a lot of C++ projects are being continuously tested every day, every patch, to find if there's a vulnerability, which vulnerability then may be taken up by the developers, or they can say how critical it is. So the thing is, generally, these issues, as mentioned, are in a whole different class because of the way they're described. Like general, you would see commonly just this report saying there's a heap buffer overflow. Somebody did a write at this location. That's how much it can give you. So we were thinking, okay, this is very problematic. Developers need to spend a lot of time. So why not create an agent that can solve these issues? We already had the outcode over agent, so the next step would be really enhancing it so that it can properly solve these vulnerabilities, specifically in OSS fuzz. Now, one important thing is that the only thing that you may not have a test suite, you may not, but you have at least one failing test input that shows that this is a true positive issue. That's the fundamental thing that you can do. So you have a very clear signal if you have solved the issue. But that does not mean that the patch will be good. So I will talk a little bit more about it. Now, we took the general code rover system, like the whole agent loop, but we modified a bit more because there are some nice things that we don't need to do. Previously, I presented how we added a reproducer agent that really was taking the natural language description, writing a test case. Now we don't need to. Now we have a real agent, so that means our reviewer can just focus on reviewing the patch itself. Just saying, okay, this patch is good, this really has solved it, or no, this patch is too general. So to give an example, let's say your program crashes on X is an input 2, but the fundamental issue is that the input is even. Generally, one of the big problems that has been shown in the research is that a lot of these systems that I talked a little bit about at the start, which are very specific with patterns, they really solve this overfitted issue, like really solving only for input 2, but they don't solve the general problem. So our research group had really done a lot of work to overcome this problem, and we still focus that we still have the vision that we should not be over-specializing, we should have general solutions that really solve the underlying problem. So CodeRover really took it in that direction where the reviewer was really focused on saying this solves the underlying problem. It's not just a random, just not solving that specific test case. So having this issue, we also applied it to real bugs, but we saw one important thing. We also have another source of information, which is the call graph. So previously I talked about the spectrum-based fault localization, which gives you the stack trace, or more specifically, the specific locations from the trace that are effective. This is not also the best thing when you have a single failing test case. The other tests may not cover this location. They may not be useful, and the spectrum may not be that effective. So the idea here is to go in a different direction where we utilize the call graph of this failing test case. So again, we're just collecting information that's dynamically, because if you just look at the crashing stack trace, the crashing stack trace tells you what is the current collection on the stack. It doesn't tell you what has already been executed. So this difference is fundamental, especially in systems which set up the environment. So let's say some of the common programs that are fuzzed are really file processing programs like image processing, audio processing. Those have a lot of setups which may not be seen from the stack trace itself. So that's where the dynamic call graph, having that provides better signal compared to just trying to use spectrum-based fault localization. Now, evaluating this in practice, we took a collection of real vulnerabilities that were disclosed in OSS fuzz. We took them and we ran the agent on them. Now, for 73% of them, we found a plausible patch. To define what plausible means, here it means that it did fix the test case that was presented. As I mentioned, just because you fixed one test case that you know failed doesn't mean you've solved really the underlying problem. So plausibility is the best we can do with an automated approach. As always, we take developers' feedback when it comes to evaluating this. Usually, we also did evaluations between ourselves, and we also decided at one point, yes, we think these patches are good, let's send them to the real developers. So myself and a couple other colleagues, we talked with developers, we submitted these patches in GitHub, we opened PRs, we said, hey, this is generated by an agentic system, this is the patch, maybe we give them some additional information and we go back and we discuss with them. We saw quite a lot of successes. Myself, even took a couple of patches were accepted. So we had like 26% of acceptance. And these are really very popular projects or very important ones. So to give an example, ASIMP is used by graphics. Some of the graphics formats, like for models, are using ASIMP to read them. libtiff is this very popular library for TIFF files, which are another image formatting. readstat is, I think, a Unix utility that also presents information. I forgot about FluentBit, but I also think it was another file processing. So we really saw that we have a system that can fix real vulnerabilities, which some of which have CVEs. So it can be quite effective for this. Now, the next step from this is that, yes, we had a system for fixing GitHub issues. We have a system that can fix vulnerabilities. But the next perspective is, what is the more general use case that we really have fundamentally? And this is where we take the next step with our use agent, our unified software engineering agent, where really the idea is that compared to the previous work where we really had specialized systems, in a way, SpecRover, it's quite set up towards GitHub issues. You have some idea of what you can use to solve these issues. CodeRover, you have a failing test case. Let's fix the vulnerability and solve this. Now, in reality, it's a lot more general. There's a lot more actions to do and a lot more problems to solve, like solving documentation, fixing issues, reviewing. So we should look at making a more generalized system. So this is where the use agent comes into it. This has been a work done together with colleagues from Purdue University, where the focus was really having a unified agent which has a collection of common actions, such as write a test, run the test suite, write a patch, collect additional context, read documentation, and all of these together are provided as inputs for a meta agent, which meta agent can reason and say, okay, this is the task. What's the next step that I need to do? What's more context that I need to gather so I can solve the issue at hand? And at any point, the agent can say, I'm done. Whatever I've generated, I can give it now to a human to evaluate. We believe that these systems can be fully automated, but we do think that there is still a human should be in the loop to evaluate, because it is important for them. Like, these systems are not miracle makers. They are very good intelligent systems, but they have very nice capabilities to save you time. Now, we also discussed about opportunities about more autonomy, where it's really, in a way, Cloud Code is one example of a full autonomy system where it can just do whatever it wants. It has the terminal, but this system still has its benefits, and it makes it easier to present to companies to apply in practice. Now, to compare with this, you can kind of see the specific workflow for this, for a specific action. Like, let's say, okay, I want to execute the test suite. What do I need to do for executing the test suite? Yeah, well, I need to gather documentation. I need to the agent has to figure out how can it run the test suite, how to install dependencies, really do all of these steps before the flow says it's complete. Now, as mentioned, there's a lot of possible problems that can be solved with this. Program repair, really feature testing, bug fixing, regression testing, test generation, partial fix improvement. Let's say that somebody has already an idea in a PR, like a pull request, and they say, okay, I have these, I've modified the code. I think this fixes the big issue. Let's say code over S. Well, the use agent can look at that and say, yes, this solved it, but you're still missing an edge case, and I'm going to modify it. So in a way, the perspective is really these systems can replace humans and help them spend less time on the problems that we see that can be tackled successfully. Now, to evaluate this, we took use agent and compared it with another popular agentic system, which is called OpenHands. The idea was that there's a collection of already benchmarks. So we have SweetBench, but people also made is WT bench, there's repo code, repo tests. These repo code and repo tests are also made from our colleagues at Purdue. The idea there was that for repo code, it was that you have been given the specific function in the code base that's missing, and your task is to figure out an implementation that is correct for it. And similarly, repo test is the same problem. Now, comparing them, we see a significant difference once we take the use agent, because again, we have a system that's very much specialized towards being a good software engineer compared to a general system that just has these capabilities to interact with the software, with the code base. So we see a lot better benefits. And this happens, of course, across different sorts of agents, different sorts of setups. Of course, our main model for this work was Entropic's Cloud Sonnet. It's really still quite state of the art when it comes to software engineering tasks. And also we had taken, I think this was with DeepSeek V3, because that was one of the newer models at that time. Now, overall, there is really a key takeaway here. There's a lot of opportunities for building LLM systems for software engineering tasks. We've talked about the very initial works which really focused on issue resolution, vulnerabilities, how to enhance trust, how to enhance give intent, and also really taking the next steps towards systems that can generally solve software engineering tasks. Now, this is really the present, but there is a lot more. It's, as you know, as they said, I think it was December last year, this year is the year of the agent. There has been a lot of agentic systems, a lot of Y Combinator startups, a lot of different research groups have presented many, many solutions. So there is a lot more. Our research group really has a lot more projects upcoming, in the works. There's a lot of opportunities to do here. So with this, I'd like to conclude and say that we at Spartan really care about automating software engineering. We believe that there's a lot of opportunities for that, but we know that we don't want to present solutions that just give something. We want to present solutions that are trustworthy, that people can use and really say, give really a stamp of honor, stamp of trust and say, this is good. Yes, thank you very much for listening. We can have a couple of quick questions. Yes?
So when you were saying the AI automates over tests, and then you mentioned very quickly it automates over the agent space of the test, what do you mean by that?
No, sorry, yes, just to phrase the question. It's not that the AI is exploring the input space for that problem. I know which specific slide you're mentioning. One moment, let me just go back. Yeah, this was part of the vulnerabilities here. Oops. This specific part, this is done by a fuzzer. This is not done by an AI.
I was asking for a slide before this. I think it was a static analysis.
Oh, the static. No, the static analysis, somebody who's not an expert with clickers. I need a moment. So the idea of the static analysis is that it finds the issues, and then these issues, because they're clear cut and they're less false positives, we can then give them to the agent. But the agent is not here generating any inputs for these issues, because these issues can mostly vary on like stylistic issues or specific faults. So the agent can utilize the test suite. It doesn't need to create inputs for this specifically. It really depends on the issue, but there's a huge class of problems here, varying from stylistic problems to architectural problems. So the static analysis can find them and it can give them to the agent. So the issue generation was for the fuzzing more, but that's not I mean, there are systems with AI. Okay, then I misunderstood you.
It's okay, we can talk about it.
This one, is it this here? No, here the agent just generates a singular reproducer test that just generates one test, and it can iterate over it or rewrite it. So it's not, I mean, you can make it generate property-based tests which explore a space. That's a recent work that our research group did, where we wanted to more focus on these sort of tests, but yeah, that we can discuss offline. Thank you. Yes?
Earlier you mentioned regarding code over as you talk
even it doesn't work.
Yeah.
And the agent, and it's a hard task to get the agent to generalize.
It has been a hard task to generalize with previous works, but with agents, we're seeing that it can generalize this. But we're saying that it can. That's why it's important. It can.
Are there methods that you know about that's why? Sorry, are there methods that you've tried to get it to generalize, or are there any insights that you have as to why agents are going to generalize?
Okay, there's two fundamental questions. Like, first question is, how can we help the agent generalize? I think that's the first question, right? And the second was
Insights as to
why it's doing it. So insights as to why it's doing it, I would say this will anger both camps. It can generalize because it has a lot of data. So it has learned the relations, but fundamentally the data has this generalization, so it has learned from that as well. So it's a bit of, I would say fundamentally it's really the data, and just that the language models are able to present structure that goes to the generalization. That's the thing. Now, we have not specialized it to say, yes, do X, Y, Z. And yes, in a practical setting, it would be valuable to maybe provide some additional guidance for certain issues. But overall, it's very difficult in that case to make it general for projects. So the models are capable of generalizing. That's why if we go to the results, and I'm not messing up buttons again, we see 73% are plausible. They are good. They solve the issue at hand. But after inspection, we see that there's a lot less. So it has generalized, but there is still more opportunity. So the question we want to be able to answer is, what's this general data that we can make it generalize better? Yes?
How does autocomplete compare with current solution like cloud codecs?
What was the second one? Codecs. Okay, so we're talking about GPT codecs, just to put it into context, because there's multiple products with that name. So Cloud Code is, I would say, Outcode Rover is really focused on issue resolution, so it's specifically made for generating patches or modifications. Cloud Code is very general, like you can tell Cloud Code, I want a whole project, and it can do it for you. So Outcode Rover was more specialized at that time because we didn't have these systems. Like there's a lot of things that had to happen for this to be doable, like tools, MCP, context windows. That's one thing. I would say use agent is closer to that, but it's still a more constrained version. So it's really more transparent as to what it's deciding and why. So I would say the end of the spectrum is really, yes, the one end of the spectrum is Cloud Code, Copilot, Cursor, where they're really free for all. They can do whatever they want. They have terminal. The models are specialized for terminals the more we see it. While use agent and everything else has been more specialized. Like at one point they were like OpenAI called them even workflows to compare with the agents. But in reality, they are agentic systems with just better guardrails.
So,
Like, do you have, like, we can...
So when they are solving the same issue, when cloud code solve the same issue as use agent or autocode, what is the expected behavior difference?
I would say that from my expectations, it would be that Outcode Rover or Code for S, they would be cheaper because they have a specialized flow. So it's also easier for you to understand how it reached that conclusion. While at Cloud Code, it can just, the model may be thinking, it has its own internal prompts. You have no idea what's going on. It just decides, okay, I will run this tool X, this tool Y, this tool Z. But then if you run it again, you may not have the same results. So I would say a bit more consistency, cheaper, overall it will be faster because we know what are kind of the ingredients used for this sort of problem. It's like if you want to go more flexible, the use agent sort of solution would be for that.
Okay, if you have any more questions, feel free to ask during the break or after finance. We have right now, sorry about that.
No problem, no problem.